welcome to our lesson on current potential difference graphs. So before you see this video, I'm hoping that you have already drawn two graphs. They should be cross graphs. By that I mean it looks like you're drawing a cross. So there's a positive side of the graph and a negative side for both axes. And I will talk you through what they should look like and what notes you need to make on them as we go through this lesson. So if we were in school, I would have got you to do an experiment where you, where you changed the current through a circuit and then measured the potential difference and vice versa. And we would have used this setup. So in this circuit, you can see there are two cells providing the energy. You've got an ammeter to measure the current. You've got a variable resistor, which will change the current in the circuit. And then you've got a voltmeter attached in parallel. So I would basically attach this all up, measure current voltage, then I'd change the variable resistor and change its resistance, and I'd measure current voltage again. And I'd go through that and I'd slowly basically fill out this results table. Now have a look at the left-hand side. You have potential difference current, fine, nice results table, but at the bottom you have negative values. Now the way you do that is basically you unplug the battery, you turn it around, so you swap the positive and negative ends, and then you plug it back in and take the same values, and it should give you negative values. So if, as I say, if we were in school, we'd be doing this experiment. My cat's just come to say hello, which means she's going to start meowing to go out the door in a second. So sorry if you start hearing her meow. I'm ignoring her whilst I do this video. So yes, you're going to change the current voltage. You would have changed the current voltage and measured them, swapped them around to get negative values and carried on. Now I'm hoping that one of your graphs looks like this. And this is a graph for what we call an ohmic resistor. And that is just basically a normal resistor. Ohmic means that it follows Ohm's law. It means that current and voltage are proportional, basically. And you learn more about that if you did A-level physics. So with a higher potential difference, the electrons are given more energy. This means they travel faster and more electrons pass a point per second, i.e. higher current. So can I please get you to title and write your notes on your resistor graph? That would be fabulous. And then we shall have a look at kind of an example about it happening. So let's just go here. So this is why it happens. You've got a circuit with a 1.5 volt cell and a resistor. You can see the electrons flowing around. If I were to increase the potential difference by adding another cell, you can see the electrons are given more energy and they travel faster. 4.5, faster still, and there you go. So the more potential difference I give them, the faster they travel. Right, the second graph, I'm hoping, looked a little bit like this. Now, if yours does not look like this, did you hear that? That was a cat, I did warn you about that. Give me a second, and I will let you out in a moment. I know she doesn't understand me, but I still talk to her. If your graph doesn't look exactly like this, please can you just slightly tweak it, so maybe go over in a different colour pen and just give it that nice S shape. The reason that it looks like this and not quite like the other one is as the potential difference increases, the current increases. Fine, so far so normal. The fast moving electrons collide with the positive ions in the wire. Now this relies on you knowing about metallic bonding in chemistry. So if you cast your minds back, in a metal you have positive ions and you have that sea of free electrons. Now in electricity it's that sea of free electrons that move. So as they are moving, they're starting to bump into those positive ions and they start transferring what we call kinetic energy. So the ions start vibrating, which means when the ions are vibrating, that's the same thing as us saying getting hot, and they get in the way of the electrons flowing through. Therefore, the resistance increases. So what I'm basically saying is, as you increase the voltage and you increase the current, the ions in the wire start vibrating, they get in the way more, the wire gets hot, the resistance increases. And that's why you get that tail off. You can't go on increasing current because the resistance has got a bit high. So again, if you could please add this to your bulb graph, that would be fabulous. Don't forget your title. And again, I'll go through a model as to why. So, why is it? Now, I'm not sure if this works particularly on the iPad. So here's electrons flowing through. You can see the ions are starting to vibrate. No, it doesn't really work on the iPad. If this was on a computer, they'd all be vibrating permanently. You'd see them kind of wobbling around the screen. No, just not really working, is it? I'm tapping a million times to get them to do this. And you can see because they were vibrating there, the electrons have slowed down. It's not perfect by any means. But an analogy for thinking about it is if you were trying to carry a tray of drinks through a party, and at the party, everyone was playing musical statues. If you were trying to carry your tray of drinks through a party where everyone was being a statue, so it was that moment when the music was off, you'd be able to get through fairly fast. Okay, you'd have to duck and dive a bit, but you'd be okay. That's like electric current flowing through a wire when it's cold. As it gets hot, the ions start to vibrate more, and that's like everyone starting the dancing bit of the musical statues, and you again as an electron trying to get through with your tray of drinks. You'd obviously have to go much slower when everyone's dancing. So when a wire gets hot and the ions start to move, the electrons and the current slows down. Right, hope that made sense, and see you later. Bye.